As you may recall, last hour that we discussed before, only now on the ocean side we have San Pablo Bay, and on the river side, of course, we have the delta. But the same processes take place, except that in this system, the cross-section of the channels have evolved to such a point that there's no net deposition up here. The tidal prism of the delta, all the surface area of the delta that has to rise and fall, is sufficient to keep the currents in the mixing zone strong enough so that there's no deposition. Unless, of course, you dig a hole or make some place that sediments will deposit. Then it will deposit very rapidly and fill back up to this present steady condition. You may have noticed that, well, you couldn't see it while we were out there, but the channel goes right through mudflats on either side in Carquinez Straits, and that those mudflats have accumulated to the point where the channel is narrow enough so that these currents keep the material suspended. But large amounts of material go through the same process in that upper zone. That has some interesting ramifications that I'll describe for you later. Prior to in 1870, 1896, 97, 1922, 23, and 1950 to 56, there were hydrographic surveys made of the entire San Francisco Bay system. These surveys were used to make a sediment balance. Actually, it wasn't quite a sediment balance because we didn't have the information of what went out through the Golden Gate. But we did have information on what arrived in the San Francisco Bay system. I'll show you in a few minutes. And we had these surveys which could be used to calculate the amount of material that accumulated on the bed of the bays. This is the apparent sediment accumulation. That is the decrease in water depth times the area of the bed in these various bays. And they're grouped together, Suisun and Grizzly Bays and Carquinez Straits grouped into an upper bay. San Pablo Bay taken by itself, North San Francisco Bay, that's the central really part of San Francisco Bay, and then South San Francisco Bay separately. And notice that going across the top row there, that between 1870 and 1896 there was 64 million cubic yards of sediment deposited in Suisun and Grizzly Bays and Carquinez Straits. Those are small bays. That's a lot of sediment. Those were the years following hydraulic mining in the Sierra Nevada. Hydraulic mining was officially outlawed in 1877, and it probably stopped not too long after that. Then in 1897 to 1922, it actually decreased from the level it had been in 1896 by 17 million yards, and further decrease in the period 1923 to 1950. The reason for that deposition was that a huge amount of fine sediment was brought down into the system and deposited there. Then during the period 1897 to 1922, wind-generated waves worked on that sediment and put it in suspension and let it circulate further down into the system. That evidently continued after 1923, as indicated by that minus 4.7. The efficacy, or effectiveness, I should say, of the wind-generated waves to suspend sediment is very sensitive to depth. So when the depth of when the water depth reached a point where the wave suspended sediment at the rates that it comes into the system, then you have a steady state circumstance. But in this case, it appears that it hadn't been reached even by 1950. Well, or at least sometime in the last period, 1923 to 1950. San Pablo Bay similarly received a huge amount during the period 1870 to 1896. It continued, there was no decrease, it continued to accumulate sediment in 1897 to 1922, and still in 1923 to 1950 period. North San Francisco Bay didn't get much during the hydraulic mining years, but then it received more during the next period and still more during the last period. South San Francisco Bay, by contrast, deepened during all three periods. Now these are apparent sediment accumulation. Sea level is rising, so you have to take that into account in making computations of this sort. And the sea level history looks like this. Yeah.
On the previous slide?
What's that?
Could you turn back to the previous
Sure.
slide? Am I wrong to see a trend where it seems like the sediment that was deposited in Suisun and Grizzly Bays it was moving out through the system over the...
It was moving out through the system during the second two periods.
So those increases in sediment, you think, are the result of the stuff that was moving out of Grizzly Bay?
Some of the sediment in San Pablo Bay is sediment that came out of Grizzly Bay.
Okay.
Yeah.
So this trend, for example, for North San Francisco Bay, that trend you
Right.
expect it to continue on forever, or it will eventually...
Well, it'll eventually, well, let's hear the rest of the story and then we'll talk about that. Okay, sea level looks like this. I told you that I think already that this is the longest continuous record of sea level in the United States. The Fort Point and Sausalito gauges there, but it's been a continuous record. And during the early years, when it appeared that sea level was rising really fast, they thought the gauge was sinking and went to heroic efforts to make the gauge one that wouldn't sink. And, you know, along about 1880 there, it looked like maybe it wasn't sinking anymore. It seemed to level off. And then about 1910 or 1920, it began to rise, and it's risen at a nearly constant rate ever since. Each of those points, the ends of each of the jagged lines, is the annual average, the yearly mean sea level. That is, it's a mean of all the highs and lows for the year. But you can see that it's not steady. It varies with time, and it increases. It apparently increased during at a rapid rate during this period, and didn't. In fact, it looks like it decreased during this period, and then it gradually assumed a level rise. San Francisco, the tide gauge was right on the edge of the junction between the eastern Pacific plate and the continental plate under the United States, American plate. And it's undergoing stress. You know, it's moving now continuously. What we're no doubtedly seeing here is the change in elevation of the land surface, not so much sea surface, at least during this period. And since that time, it's risen at about the rate that you expect sea level to rise to occur, at about 0.7 of a foot per century. It's really the relative elevation of the sea and the land, and either one, of course, can change this record. But as far as we're concerned, we want to know what the rise of sea level, what contribution the rise of sea level made to that change in sediment volume that came in. So if we correct for that change, then we see a slightly different table. And here they're grouped together to show what they are. In the top, get up here. In the upper bays, incidentally, the first period isn't included here. The second two are. Forgotten why the first two weren't included. There was some reason the data didn't provide. Anyway, the second 2 years are about the same. Notice that there was the corrected value still showed a slight decrease in the volume in Grizzly Bay, Suisun Bay, and Carquinez Straits. In San Pablo Bay, the actual accumulation was about 2.3 million cubic yards, and then less in the latter period. North San Francisco Bay actually increased. That is, the sediment was suspended by wave action and carried down into San Francisco Bay during that period. And then if you take into account the volume of sea level rise, it looks like the total is about the same for the two periods. That is, the material moved down, and the amount that comes into the system is equal by the amount that goes out in that portion of the system. In South San Francisco Bay, there's actually net increase, net loss of sediment. Some of the sediment down there is being suspended and carried out. And the reason for that is that the supply is limited, and the material that gets down there is very fine and is easily suspended and carried out. Well, this is the beginning of a balance. Now, if we take the amount of sediment that comes in,
What's the reason of the difference in the sea level rise velocity?
1.96, the volume of sea level rise? Well, the volume of sea level rise is the change in elevation of the water surface times the area of the system. And the area of the North Bays is different from the area of the South San Francisco Bay. Any other questions about that?
So South San Francisco Bay is actually losing. So South San Francisco Bay is losing sediment.
Losing sediment, you know.
Is that
Well, now it may not be losing sediment. The groundwater formations are collapsing down there. There's actually subsidence in South Bay, and that must contribute to some of that. The curious thing is that it's the same for the two periods, though. In 1922, I can tell you for sure that water was still flowing out of the tops of wells without being pumped. You know, there shouldn't have been any dewatering at that time, but it may have contributed to that. Since that time, there's been a lot of subsidence, as much as 8 feet. Well, if we somehow in there, a second. Oh, we can estimate the amount of sediment that comes into the system by looking at the hydrographic data. We have data at that time. We had data from 1921 to 1960 to 1960, and that is water discharge data from the San Joaquin River and the Sacramento River, and from the eastern streams that come into the delta. We only had suspended solids data, however, for the period from 1957 to, that was added to later, to should be about 66 or thereabouts in there. So it was necessary to relate the water discharge to the sediment discharge. And it appears that you can relate both the San Joaquin River data and the Sacramento River data on one line. From the right of that vertical dashed line is Sacramento River data, and to the left is San Joaquin River data. They seem to fit pretty well on the one line. So applying that relation to all the hydrographic survey, or all the water runoff data from 1921 to 1970, provided a means of estimating the amount of sediment that comes in. And of course, we're interested in the periods that we saw those charts. And doing that, we can come up with a distribution of water coming in using the hydrologic data and the sediment supply coming in. I'm going to come back to these two figures, but first I want to go back to the balance. Knowing that, we can calculate the amount of sediment that comes into the system on the average over a long period of time. And that leads to this sediment balance here as of 1956. There's about 8, on the upper right there, you'll see 8 million cubic yards in delta outflow, and about 2.5 million cubic yards from other tributaries, Petaluma River, Napa River, and the other Santa Clara River, and so on. So that makes about 10.5 million cubic yards coming in. There's about 1 million cubic yards of dredged material are disposed on land, so that's taken out of the system. The amount of sediment dredged and dumped back in the water somewhere else is about 7 million cubic yards, so it stays in the system. And then down below that, you'll see about 2.8 million cubic yards is accounted for by loss of water system, and about 2.6 million cubic yards due to sea level rise has to be corrected for. That leaves about 5.4 million cubic yards net deposition in the bay system, and about 5.1 million cubic yards going out to the ocean. So it's not really a balance. We get the amount going out to the ocean from the difference between the other two. Now, I say that without any apology. There's a tremendous problem in determining the amount that goes out through the Golden Gate. There are people very much interested in doing that. It may be that the necessary funds will be put together to do it. But the currents through the Golden Gate are like 10 to 12 feet per second. It's about 300 feet deep. And the currents along the shore are very complex, and there's lots of eddies and so on. Ask any fisherman that goes out there. He'll tell you about it. So measuring the suspended solids discharge through the Golden Gate, and keep in mind it's a reversing flow, so you have to measure it in both directions and take the difference. And as soon as you start taking differences, you're running into difficulties. So there have been various estimates made, and I think that one has stood the test of time. We're now in the process of making another sediment balance, or another sediment computation of this sort. And I just received last week the inflow, the data for the inflow that can be reduced to get this kind of information. We've completed the estimates of the change in the bottom, and within a few weeks we should have a new balance for the later years. A hydrographic survey was just completed in 1990, and we're using that data. So we have a system where the sediment is coming into the system in the wintertime, circulating around through the system and depositing in various places, some of it being dredged and disposed in open water, and eventually either finding a place where it stays on the bottom where it's not again resuspended by wave action or currents, or going out to the deep ocean. Now the amounts that come in are widely variable. This is the water flow again, and if you look up there, and the three plots are the freshwater, the freshwater inflow for 1960 water basin conditions. That is, for the diversion works and pumps and irrigation practices and reservoirs that were in place in 1960. We took the entire record from 1921 to 1966, I think it was, and treated it, processed it as though the system that was in existence in 1960 had been in existence the whole time. And that gave us a distribution. And notice that it ranges from something a little below 60 million acre feet per year at 2% of the time, at 2% of the time, it's something like over 50 million cubic acre feet per year. And 2% of the time, it's about 4 million acre feet per year. That's a wide range in water flow. And as you can appreciate, when the flow is low, if the demand is up in here, we have what we call drought. And that's what we've been having lately. The drought is really the relation between the demand and the supply. The second row, the triangles, is for conditions in 1990, the conditions that were proposed to be in 1990. We operated on the entire runoff record as though the supposed 1990 conditions had prevailed the whole time. And then the circles are for the 2020 conditions when the water project was expected to be completed. Interesting thing is that this plot was made in 1966, with data available in 1966, and it's about what we're seeing now. 10% of the time, the flows would be a minimum flow, and at that time, the minimum flow was supposed to be 1,500 cubic feet per second, minimum outflow to the bay system, 1,500 cubic feet per second. Now it's kept at about 4,000, so it would be a little bit higher. Now, for the 2020 conditions, and these were operating conditions determined by the Department of Water Resources and the Bureau of Reclamation, 40% of the time there would be a minimum outflow. That means 4 years out of 10, we're treating this as though every year is independent from every other year. 4 years out of 10, there would be these minimum flows, or 0.4 times 0.4, 0.16 of the time, or 1 year out of 7, it would happen one time out of 7, happen 2 years in a row. We're talking about low flows into the San Francisco Bay system. Well, the sediment inflow plot looks similar to this one. We're talking about, now this is millions of tons, not cubic yards. The average is about, for the previous slides, was about 4 million tons per year. You get 10 million cubic yards. So we have something like over 10 million cubic yards per year under 1960 conditions, and down to about 0.6 of a million tons per year, 2% of the time. Quite a wide range flow under 1960 conditions. Under the future conditions, 40% of the time, just as before, we'd have these very small supply of suspended sediment coming into the system. So we're dealing with a system that has a widely variable sediment supply to it, and that variability is worsened by the fact that we're diverting water, fresh water, and sediment in the water development system. The impact, there's several important features of this system, of this plot. First of all, if the supply of sediment coming in is less, then the amount of dredging that we'll have to do is going to be less, right? There's going to be less sediment in motion, so you expect lower sedimentation rates at wharfs and in harbors and so forth. That's to the good. To the bad is the fact that the suspended solids in the bay is the limiting factor for the multiplication of algae, floating algae. When the waters become brown in the winter, you don't see much algae. When they clear up in the summer, it begins to get green, and it gets greener and greener. And in areas where the flushing rate is low, then you see significant levels of algae growth. We were worried in 1966, when this was done, about algae growth and anoxic conditions in the bay. Chesapeake Bay, as you may know, becomes anoxic every summer. Most of it does. And that's because the light penetration is appreciable, and there's a large source of nutrients in the bed from waste discharges primarily. And of course, that's, as far as the water quality for fish is concerned, that's a major detriment to the water quality. Well, the flushing in most of San Francisco Bay is sufficient so that so far we haven't had anoxic conditions that we know of. For a while, it looked pretty bad down in South San Francisco Bay, but that's improved some. Nevertheless, it's of concern, primarily because the San Francisco Bay system is so shallow. You can visualize it this way. At a typical suspended solids concentration in 1966, the euphotic zone, that is the depth to which light intensity was sufficient for the multiplication of algae, was about 1 meter. And if you reduce it proportionally to this, reduce the ambient concentration proportionally, then the depth is about 5 meters. The average depth is about 5 meters. So 20% of the depth is sufficient for algae, has sufficient light for algae multiplication. And it's pretty well mixed. So an algae cell will see light a fifth of the time during the daytime, and not at all at night, of course. Now, if you reduce the suspended solids concentration proportional to the projected decrease in sediment coming into the system, the euphotic zone will be about 3 meters, or 3/5 of the time, 60% of the time during the daytime, the algae cell will be in light sufficient for its multiplication. So you can see that the suspended solids concentration has a major impact on that. A second reason that it's relevant to water quality is that the sediments have a large sorptive capacity for dissolved materials. The cation exchange capacity of these sediments is about 30 milliequivalents per 100 grams from the mixture. And they can absorb huge amounts of dissolved materials, and do, in fact. That's caused a a lot of concern about dredged material disposal in open water. The material in Oakland Inner Harbor is polluted because it absorbs waste that are discharged from the local discharges. Well, the assimilative capacity provided by the absorption of dissolved toxic materials on clay sediment particles is large. I've estimated once that it's about as large as all the flushing by seawater and freshwater outflow put together. It absorbs these particles and carries it with it to some final resting place out in the ocean or in the bottom of the bay. So if we reduce the sediment input that much, we have some serious water quality problems. We had 14 months of water rights hearings, State Water Resources Control Board, in 1971, 70 and 71. And these figures were actually prepared before that time, and I presented them to the board and said, you'll have some serious water quality problems and better look out for the fishery. Well, the water quality problems are as bad or worse than I said at that time, and the causes are a combination of this sediment, reduction in sediment outflow, and the reduction in freshwater outflow that reduces the dilution and transport capacity in the main migratory pathway, that is up through Carquinez Straits on up to Chips Island for migratory fish. There's a lot of heavy industry all along those shores that discharges wastes in that region, and by reducing the freshwater outflow and reducing the dilution and reducing the sediment supply, decreased the assimilative capacity of the system for these wastes. Well, the importance of suspended sediments to water quality is just now being appreciated by the regulatory agencies, and it's not very well understood. We have a few models that represent it pretty well. Keep in mind that in that section of the bay, the reach between Carquinez Straits and Chips Island, is the mixing zone, where we have the sediments going up and mixing. So it's an area where waste can be absorbed readily. The system favors the absorption of waste, and I'm sure it's been very effective in the past. Here are some estimates made in the, I've mentioned before, 4.38 million cubic yards in 1960. Under 1990 conditions, 2.82, so it goes down to about half in 2020. These are average annual sediment production over that period of time. So in the average, we're talking about an appreciable reduction, but keep in mind that variability that I showed you before indicates that there will be times, years, 40% of the years will have very low concentration, and it's those times that we have problems. The fishery, once you kill off the fishery, it's awfully hard to reestablish it, so it's those times that are critical. I showed you the plot of sea level rise earlier, and one of the points I didn't show was that there's quite a variability from year to year. And this variability results from a number of things. Freshwater outflow can affect it some years where you have unusually high freshwater outflow. Winds, the wind patterns on the ocean affect it, gives wind setup, and and of course various oscillations, noises in the ocean basin system affect it quite a bit. So that when you average it, it doesn't really take out all the fluctuations. Notice, however, that the scale is pretty small scale. This is 8.4 feet, 8.5 feet, 8.6 feet. So this is 1/10 of a foot we're looking at in the units here. I put that on because it has two effects on marsh growth. So what I want to talk about next is the sedimentation around the margin. That is the growth of marshes in the shallow areas around the side. The reason for talking about marshes is several-fold. One is it's a sink for sediments. It's one of the places sediments go. The second is that there's a lot of public interest in marshes at present. The president has a no net loss in marshland policy. If you read the read the Chronicle, you'll find, or almost any paper for that matter, you'll find that there's a lot of controversy about the president's sincerity in no net loss of wasteland. And let me tell you what that's all about. Landowners, like the owners of the land north of Highway 37 that we drove by Saturday, want to develop their land. That is, if there's some way that they can make money on it, they'd like to do that. Either agriculture, either for growing things, or build houses and sell them, or industry, or various kinds of uses of their land. Landowners are usually in the position of having paid something for the land to begin with, and they paid taxes on it from the time they bought it. So they feel that they have a vested interest in the land. It's theirs, and they want to use it. That's one side of the picture. The other side is the people who are interested in wildlife and preserving wildlife, particularly waterfowl, migratory fowl, and they want to preserve at least enough habitat so that the flyways are preserved. We're in the Pacific flyway here. Birds come from down Central America or so and go clear up into Alaska. And if they don't have resting places and places that they can get food along the way, the flyway will die. So it's maintaining a sufficient amount of marsh area for the migratory birds is a very important consideration. Then there are the group that like to go out and catalog birds, go out and see birds and various wildlife kinds of wildlife, and they of course have interests that need to be protected. So we have these two groups of people who own lands that might be called wetlands, who feel that they should have a right to develop their own land, and those that recognize the fact that we've developed so much of the marshland that now we're in danger of not having enough. That's something that sounds like you could handle it easily. The problem is that those who catalog marshland, or wetlands, I mean, call anything that's wet a wetland. I think they'd call a parking lot a wetland if it stayed wet for 15 days of the year, or 7 days of the year. That is, any field that has a puddle in it, that's called a wetland, even if it only lasts a week or so, and is dry all the rest of the year. Well, you can see there's going to be a lot of controversy if you own land that just has a spot in it that gets wet, and you can't develop it because of that spot. You're liable to go out there in the middle of the night and fill it in, kind of thing. So the controversy that you're hearing about, Mr. Riley, head of EPA, promulgated a trial set of wetland definitions, wetland definitions. And there was a huge cry out of the people that want to develop their own lands objecting to that. And the last one had 15 days of, if water stood on it 15 days, it was called a wetland. Well, 15 days is 1/26 of the year. It's pretty hard to call something a wetland if it's only that long. So they're not really talking about marshes, even though in the TV news what you see is pictures of marshlands, that really are wetlands. That's not what the controversy is about. The controversy is about the other lands that some people call wetlands and others call agricultural, or usually agricultural or grazing land. Then there's another aspect to it. If the lands are called wetlands and can't be developed, but called wetlands by the government, and development is prohibited, that's a taking of the value of the land without compensation. Do you follow me? So the issue there is, who's going to compensate us for this land? Federal government that made the rule? Seems reasonable way to do it. This issue has been around for a long time, much longer than the issue of the wetlands. I'll describe some cases to you later where where lands have been paid, taxes have been paid on lands for more than 100 years, and it was taken from them because it was, well, I'll tell you about that before the hour's out. In any case, it is important to preserve lands for waterfowl, for the flyways, and for recreational use. About 90% of the original wetlands, real wetlands around the San Francisco Bay system, have been developed. So there's only 10% left. You know, it is a serious matter, and I'm not trying to persuade you one way or the other. I want you to understand both points of view. The question comes up about, in dealing with wetlands, well, who owns them? You know, does the person that's been paying taxes on them own them, or does it belong to the federal government or the state government? And the reason that that's an issue is that historically, lands that were tide lands between mean high water and mean low water belonged to the state. Well, they were given to the state by the federal government. Originally, it all belonged to the federal government. But the land below mean low water still belongs to the federal government. That is navigable waters. And of course, below mean low water, that is navigable water. Land above mean high water belongs to whomever got it, either from the state or from the Spanish in California, whoever owned it previously. You know, if they bought it, then it belongs to them. So the issue is, what lands actually belong to the owner and what lands belong to the state? The lands between mean high water and mean low water belong to the state. So the question comes about, well, is a marsh plain above mean high water? You know, even though the owners have been paying taxes on it, the Leslie Salt that harvests salt from the salt waters up there that we saw, they claim to own that land. And the question is, when it was diked off, was it above or below mean high water? It was diked off in 1870. So, you know, it's quite an issue. The State Attorney General's office has been bringing suit against marshland owners that they think, where they think that the elevation of the marsh was below mean high water, and taking that land from them. It's a pretty serious matter. You know, we're talking about valuable land around the San Francisco Bay. You know, land is now selling for about $15 a square foot. It's pretty expensive land. So the State Attorney General is going around finding land that they claim was below mean high water in 1850 or before it was developed, or presently below mean high water, and saying it's theirs. So the issue is, was it or wasn't it below mean high water in 1850? What I want to describe for you now is a study to identify the elevation of the land between 1850 for a particular case. Amy?
Is there some significance to the year 1850? Is that when the
Well,
law was passed?
the significance is that if the land is diked now, you can't tell. It shrinks when it dries, you know, so it's lower. It's obviously lower now, and of course, you know, if you use present day, that would automatically be the state. But the defendants want to say that, well, when it was diked off, it was above mean high water, or that it would be above mean high water now if it hadn't been diked off. Those are the real issues. So I want to describe a little study that was made for one of these cases. There have been a lot of these cases, but this is for one of them.
Great. What happens with this rising sea level?
Well, that's why I showed you sea level rise. I want to next describe for you the genesis of a marsh, so that you can see now what. First, I want to tell you why you're concerned about this. Second thing I want to tell you about is, well, that's one of the reasons you're concerned. The other reason is that we're interested in converting some reclaimed lands back to marsh, and in order to do that, you need to understand how marshes grow. Those are the two reasons. So if you want to successfully convert land back into marsh, or make a marsh out of land that is not marsh, you need to know the processes involved, and they're primarily sedimentation and biological processes.
I'm a little confused about the entitlement. I'm clear that above mean high water, whoever has it, that's theirs, and below mean low water, it's the state's.
The federal,
Federal.
yeah. It's federal. Below mean low water, it's federal. Yeah. And between the two, it's the states. Because the federal government gave the states that tide land.
But this band was moving uphill over time.
That's right. That's right. So
Federal jurisdiction.
that's exactly right. That's right. Well, of course, at the bottom of the base, yeah, that's exactly right. If you live long enough, you'll see it. You know.
But between 1850 and now,
Yeah,
it's a foot, I guess.
Oh yeah, that's almost a foot. Yeah, that's quite a bit. You know. Okay, so those are the reasons for worrying about how marshes grow. Now, the way marshes grow is rather curious. They don't grow out from the shore; they grow up. And what happens is that you have a mudflat along near the shore that accumulates because of an exceptional amount of mud supply one year that creates this mudflat. And then if it's exposed a sufficient portion of the time, well, I'm sorry, you have some years you have an exceptional amount of mud that makes a mudflat near the shore, and some years you have these changes in sea level rise, these fluctuations I just pointed out, that make the mudflat exposed more of the time than it might otherwise be. When that happens, Spartina takes hold. Spartina is able to withstand inundation a significant part of the time, but it has to be exposed also a sufficient time for it to be aerobic, and it grows. And once Spartina starts to grow, then the presence of all those little blades of grass greatly enhance the rate of sedimentation among them, so that the marsh I'll exaggerate the vertical scale a little bit. The tide may range over a band like this, and if you have a supply of mud here, say something like this, then Spartina will take root on that, and as soon as there's a stand of grass there, flow through all those blades of grass, causes eddies, promotes aggregation, and protects the surface from erosion. So you get an increase in elevation there. Deposition is enhanced. And of course, as it's enhanced, its frequency and duration of inundation is reduced. You follow me? In other words, if you have a tide, something like this, if the elevation of the marsh is at this elevation, then it's inundated for this portion of the time, this period of time, and as it gets higher, it's inundated for a shorter period of time, and eventually it's inundated less. Well, depending on the frequency and duration of its inundation, the rate of sedimentation will decrease. That is, as the frequency and rate of duration decrease, the rate of sedimentation will increase because there's less sediment brought onto the surface, and it's there, the water's there for a shorter period of time, so the rate of rise will decrease. And eventually it will rise to some level, depending on the supply of suspended solids in the water that flow over it, to some level where it just keeps up with sea level rise. That is, if it gets too high, then it's not inundated very often. And sea level is in a rising sea level circumstance, when sea level gets a little bit higher, it's inundated more frequently, so the deposition rate increases, and it will rise. So depending on the suspended solids concentration, the elevation will establish of the surface of the marsh will become established relative to a sea level datum, and as that sea level datum rises, the marsh will rise. The marsh surface will rise. And if you have a gently sloping shore like this, then the marsh will encroach further and further into the shore. So the marsh grows upward and shoreward. It doesn't grow outward. In fact, as you saw Saturday, it's being eroded on this outer end here. It grows upward and shoreward. Now, it's a little more complicated than that. When the mudflat first develops, let's say, looking at a map now, this is the shore right about here, and the mudflat forms out this way. Before plants are on it, the drainage patterns are just nearly perpendicular to the mudflat, like this. And as the plants accumulate on this surface, of course, water drains into these little rivulets. But as it grows shoreward, as it advances shoreward, as the marsh level rises, then it has to drain all of these sloughs. And these erode headward, that is, the end of them erode so that they work into the developing area. And of course, the cross-section here becomes a little bit larger because the amount of water that floods and drains the surface of the marsh increases. And of course, as it gets further back up into here, you can expect this headward growth to continue. Now, when the sediment-laden water enters these sloughs and floods the surface, it drops out most of the material, or it drops out material more rapidly right along its side. The higher concentration material deposits right along its side. And so there's a slightly greater elevation right next to the waterway here, to this rivulet, than there is elsewhere. And of course that means that there will be a slight basin between them, and this headward erosion will occur where that basin is. That is, it'll curl around and try to drain that basin. And the result of that process continuing leads to a very complex, sinuous pattern. This is the bay out here. This is that little cliff like we saw before. And these are the sloughs. And you can see that they're winding, and that the branches wind a lot, and the branches have branches on them. And there are lots of little narrow sloughs. These sloughs, the little small ones, have a dendritic pattern. That is a branch and branch kind of a pattern, with the result that the whole area is flooded and drained pretty uniformly. That is, wherever there's a low spot, there's headward erosion into that low spot, so that then it is flooded. And the result is that the whole marsh plain will have a variation in surface elevation about this much, just a few tenths of a foot, a variation in surface elevation over this whole area. This marsh is on east side of South San Francisco Bay, about at the Hayward Bridge. The San Mateo Bridge, near the San Mateo Bridge. And you can see marsh has developed way up there. That's hills, the beginning of foothills back there. These are little Coyote Hills, for those of you who are familiar with the east side of South San Francisco Bay. In any case, we have these very dendritic patterns. If you compare the maps, this map was made with a plane table in 1860 or thereabouts. If you compare the maps made in the middle of the last century with maps made today, you can overlay them, and these sloughs are in exactly the same place they were then. These are not meandering channels. These are channels that meandered in their formation. And if you look at the walls of these channels, they're really vertical. They're, they may be caving off on top. They may erode a little bit underneath and cave off on top. As the marsh area increases, as I mentioned earlier, this area, these channels enlarge their cross-section so as to carry the larger flow. And so you will occasionally see a channel that looks something like this on top with pieces here falling off into the channel. But they have pretty much vertical sides. And in particular, these small channels, the little ones like this here, will be perhaps as wide as your foot and 4 feet deep. The marsh actually grows up, and those channels preserve themselves. That is, they have these vertical sides. It makes it hazardous to walk on sometimes in the old marshes. When in 1941, Easter 1941, I rode across the bay with an old duck hunter into one of these sloughs, and we camped. It was just, at that time, there was not much going on out here. We camped on the side of one of those sloughs in his boat. And in the morning we got out and walked around on the surface of the marsh. And we were hunting for timber from old wharfs and things to build his duck club. And the boat was about this far from the edge of the bank, and I went to get on the boat, and there was grass out there, and I stepped in this grass and went down between the boat and the bank, and right there I went over my head in water. You know, the bank is that steep. It's just straight up and down on the sides. It's awful dark down there and cold. In any case, the channels stay there, which is evidence of the fact that the marsh is growing upward like this, and the fact that it's so level, it's so uniform in its elevation, supports the interpretation of this growing. Well, anyway, the Deputy Attorney General asked me to tell him whether it was higher or lower than mean high water in 1850. So I prepared a little model, just a zero-dimensional model, that is a model upward. The marsh plain is so uniform that I felt that, well, if we could show rise and fall, and we were concerned in that case, particularly with near this edge, so there wasn't much loss in elevation in the channels, flooding and draining. So the model that was used was simply a model that said that the amount of material, y is the elevation of the water above the elevation of the marsh, c is concentration, t is time, settling velocity, and concentration. I think everything else is, C0 is the concentration of suspended solids in the water coming over the marsh. So this is just a mass balance of the water, the amount of water going in and the change in concentration in that water. Settling velocity times concentration is the flux, and this is the concentration times the change in water elevation. That's the amount that comes in or goes out. And of course, as water leaves the marsh, the concentration is the concentration of whatever it was. As it comes in, it's the concentration of the water being supplied. So while it's rising, dy dt is rising, then C equals C0, and when it's falling, C equals C. I used the same settling relation that we've discussed earlier, and this is just the difference equations that get that, and a sinusoidal tide, because the time that this marsh is covered by the tide is just the tip of the tide curve. So I didn't make a more elaborate one. That sign represented it pretty well. Then used actual tides for a year. I selected a year's tides and put the actual tide elevations in. That gave me the amplitude of the sign. And then put in, I forgot to say, we had measurements of the elevation of the marsh in 1963, 1970, about 1970 and 1976. So we had some basis for calibration. These are the same things you saw earlier, the sea level values, but without the lines between them. And that is just the average annual sea level. And I fitted them with two lines. One is that first steep part, just a least squares fit, and then the current value. And it's interesting that these intersected about I think it was 1860. Oh, we also had a measurement at 4 feet, and we dated that sample of the marsh 4 feet down, which contained plants that had been covered by sediments, of course, as having been there in 1454. So we had 4 points that we could use to calibrate the model. And I put in the actual sea levels with that assumption, and came out with a historical elevation of the marsh as shown by this dotted line. The straight line is just a line put in there to so that you can see the change in elevation with distance. The results came out as shown here. It rose more rapidly because sea level was rising more rapidly during those early years. And then as the rate of sea level rise became steady, then the rate of rise of the marsh became steady. If you compared the elevation of mean high water to the elevation of the simulated marsh, however, you can see that the marsh elevation was below mean high water during these early years when the rate of sea level rise was fast, and then was above mean high water during the remaining years. And the fluctuation is due, of course, to the fact that sea level was fluctuating during those years. Well, that's an extremely simple model of a marsh that incorporates the formation that I described earlier. Now I'll have to tell you what really happened. We met the state deputy attorney general and another consultant, a couple of other consultants, and I met frequently on this case. And this was a Leslie Salt case in South Bay. And at each meeting, I would say, "This is a senseless lawsuit." Doesn't sound like a very good consultant. This is a senseless lawsuit. There's obviously an edge to that land out there, and it seems to me that ought to define the use of the land, not some arbitrary thing like what sea level was, that it ought to be just that little escarpment on the outer edge of the marsh. The rest is marsh, and if it's going to be used as a marsh, it ought to be used as a marsh, period, or it ought to be developed. It ought to belong to Leslie Salt. And the lawyer named Bruce Fleischman, we're pretty good friends in spite of all this. He'd say, "Well, state wants this marshland, and if the title isn't correct, then we should take account of it." A typical lawyer's position, I guess. Anyway, at one of these meetings, I was saying that we oughtn't to be arguing about something as small as a few tenths of a foot. You can see that I didn't point out the scale there, but the difference is we're talking about just a few tenths of a foot one way or the other. And finally, one day, at one of our meetings, he said, "Well, Ray," he says, "how much is above mean high water and how much is below?" And I said, "Well, the sloughs are obviously below mean high water. And there's that little ridge above mean high water right along the edge of each slough. And maybe in between there's, it might be a little bit below mean high water." "Well, how much?" He said. "Well," I said, "half, maybe half above and half below." Kind of a Solomon-like decision. Well, about a week later, I got a phone call saying, "Ray, we settled the case." And I said, "You did?" And I said, "What did you settle it for?" He said, "Half. Half's the state's and half's Leslie's," just like he said. The other interesting aspect of that case is that the lawyer for Leslie Salt is one that I consult with frequently. And in fact, that firm and I have won some really good cases. So it's kind of a old boys situation, where the fellow on the other side said, "We should have tried that case. I think we could have won it." Well, anyway, so much for marsh elevations. If you're going to do that for a marsh far inland, then you want to simulate the flows up the channels because the amplitude of the tide is less as you go landward. And furthermore, if you want to simulate the flow through the marsh, like you're doing, then you have to take into account the sedimentation from the marsh edge in. Now, typically in an area where you have high suspended solids concentration, the concentration of water going over the edge of the marsh, over that escarpment, is high enough so that you get a more rapid rate of rise there. It actually slopes up right on the... I should have shown you some of those. It may actually slope up like this and then the escarpment out here because of when the high water flows over the top, it deposits material out here. Interestingly enough, if you look at these, you can often see layers, suggesting that there have been episodes where the suspended solids concentration was unusually high. Well, I guess discussion of marsh wouldn't be complete without talking about reclaiming marshes, or making land back into marshes. And there are several approaches to doing that. The one that I espouse is provide conditions for the plants that you want to grow. You know, if you want salicornia, then you can put sediment in there, and salicornia will grow. I've seen lots of salicornia growing, the pickleweed that we saw, growing on old dredge material. So you can just put lots of dredge material in there and have it. If you want spartina, then it has some peculiar requirements. One is it needs fresh sediment. You can't put it on old sediment. It doesn't grow very well on old sediment. It does to some extent, but not as well. So you want to provide a water depth where fresh sediment can accumulate, and then before the spartina begins to grow. You can usually do that by going out and surveying spartina as a function of elevation in nearby areas, and then you'll find it grows to some limited elevation, lower elevation, and then provide water depth, say 6 inches or so below that elevation, for sediment to accumulate. Make sure you have a supply of sediment nearby, or of course that won't work. The existing marshlands are strongly affected by the upstream development, and I think I can illustrate that best with this figure. If the land is diked off, say here, across here, then these sloughs won't have the amount of water flowing in them during flooding and every tides that they had before, because there's much less area being drained. And as a result, they'll fill in with sediment. So what you'll find is like Hirt Marsh. It's just north of the marsh that we stopped at Saturday. Was cut off like that, and the channels filled in. The people that had the marsh, the Audubon Society, wanted to reestablish those channels, but if they wanted to dig them out, but if they reestablished them, they would just fill back in again. So they finally came to the conclusion they wouldn't do that. And you'll find a lot of them around any bay where there's development, Chesapeake Bay, San Francisco Bay, wherever there's development and diking off, you find that the sloughs fill in, and that the flushing isn't nearly as good. In many diked lands, as I described, the land surface elevation falls as the soil dries because of shrinkage. You can just open the dike and let water in. And if there's a supply of sediment, which there often is in the shallow areas of the bay, the sediment will accumulate there. And you can calculate its deposition rate pretty easily and calculate the time it will take for the sediment to accumulate to the point where spartina grows and the marsh will become established. It'll grow very rapidly once spartina is established because of at the lower elevation it's flooded frequently, flooded with every tide. So it'll grow very rapidly. 10 years or so we'll often see a marsh established so that it's now in steady state relative to sea level. Precautions you have to take are make sure you don't make mosquito traps, and that you provide aesthetically pleasing waterways and a stable system. You know. Well, I can show you.
Could they possibly cut channels between lower channels to establish some sort of circulation?
Well, you need the main flow through these channels, the large flows through these channels, are the flows that flood and drain the surface of the plain, marsh plain. And if you reduce the area of that plane, then you reduce the amount of flow going in and out. If you connect them, you won't increase the...
I was thinking of wind maybe driving the current in one direction.
wind will drive it a little bit, but not enough to keep them open. Well, I've got time to just tell you one more story. At one time there was a group, well, I said earlier that I would describe a situation where people had paid taxes for over 100 years and lost their land, or lost some of the use of their land. In the 1800s, the State Lands Commission would give title to land by means of a process called patenting. It's just like staking out a mining claim. If you went to the State Lands Office with a plot showing the lot that you wanted title to and paid a filing fee, and nobody else owned it, and paid a filing fee, then it was yours. And so the bottom of South San Francisco Bay, and much of San Pablo Bay, in fact, was patented that way. And all the shallow part of South San Francisco Bay and San Pablo Bay was patented. And people that owned it just paid county taxes on it and hoped someday to develop it, to fill it in and make usable land out of it. The Ideal Cement Products Company bought up these patents and mined the land for calcium carbonate shell with lots and lots of oyster shell in it, and they just mined the shell for chicken feed and use of calcium carbonate. And they did that. In fact, they're still doing it. They did that for a long time. But then a consortium was formed with Ideal Cement Products Company, Chase Manhattan Bank, and Crocker Land Company. Got together and they decided that they would fill in South San Francisco Bay, the west side of South San Francisco Bay, from the San Francisco Airport to Palo Alto. And they had title to virtually all of that land, all those patents. And they, of course, realized that that would be very valuable real estate. They purchased the equipment for moving Mount San Bruno out there. They were going to take Mount San Bruno and put it in the bay. They had all the earth-moving equipment and everything before I got involved in this case. And that was before Bay Conservation and Development Commission had been established. The State Attorney General's office felt that that was not a good thing. In fact, they took the position that the land had been subject to the public trust, that is, people could go fishing or hunting or whatever out on the bay, and that right now belonged to the public, and that they would lose that right if they filled it. They also said that the land didn't belong to the state to give away. That's a little more convoluted point, but the fact is that the land below mean low water never did belong to the state, and the fact that the state patented it and that the people had been paying taxes on it all these years, too bad. So the issue was, there were several issues. What was the mean lower low water line? Oh, the other issue was, there's something in the law that's a little vague, but it says that if man alters the accumulation of sediment, then that doesn't count. Or if it's ebullitive, doesn't happen. If it happens during a storm or an earthquake or something, that doesn't count either. But otherwise, if there's a gradual accumulation or erosion, then the boundary of the land changes with that accumulation and erosion. So they wanted to know the last natural mean low water line from the San Francisco Airport to Palo Alto. And that was a real challenge. The slope is so flat out there, about 1 foot and 500 feet. So if you're off a foot in elevation, the boundary's off 500 feet. And not only that, it's the boundary between muddy water and watery mud. I mean, we're talking about a pretty tenuous situation. Well, we made a major study of that over a period of several years and came up with a last natural mean low water line for them and for the state. And during all this study, there was a lot of negotiation with the other side, with the people on the other side. and Crocker Land Company and Chase Manhattan Bank lawyers, high-powered lawyer and high-powered crew. And they finally settled on the line that we drew, the Army low water line. And that gave them 26% of the land that they was patented, only about a quarter, and they can never fill that quarter that they own. And the boundary of the shore that exists now is going to be the permanent boundary. That is, whether it fills or doesn't or erodes no longer matters. It's a fixed boundary. The State Lands Commission approved that, and the court, it had gotten into court by that time. The court approved it also. And the court hearing was an experience I'll never forget. We had a room full of charts and aerial photographs, and you can imagine cores, just all kinds of displays. And it was a regular trial proceeding. And the judge got very involved in the sediment business. He was really intrigued by it. And of course, every question he asked, we had charts that we could put in front of him and explain what went on. And finally, at the end of the day, it turned out we guessed the other side's approach accurately and were prepared for it. At the end of the day, the judge, just one day, the judge said, well, I'll render a decision in 30 days, and walked out of the courtroom. It's San Mateo County courtroom. It's a big courtroom. And he walked out of the courtroom. And of course, all of us just got in the center of the room, and we were all talking about the case and talking with the other people on the other side. And the judge burst back into the room, and he said, you know, he says, I forgot to ask any questions of the law. He said, but what's the law that applies in this case? And our Deputy Attorney General said, that's all presented for you in your brief, in the brief we provided you. He said that there's no controversy. We don't have any controversy with the other side with regard to the law. So he says, okay. that was it. And he proved our position. So anyway, that's south side of South San Francisco Bay, west side. Well, and then, of course, that was a precedent so that the east side wasn't filled either. So we managed to preserve the bay. Well, along the way, I forgot to mention, the BCDC was formed immediately after we started. And it was formed for a period of 5 years, a trial period of 5 years. And it was to be renewed if it was satisfactory after 5 years. The other side lobbied the state assembly to kill the BCDC. They also lobbied the assembly to not provide the $1.5 million that we asked for to make the study. So there's a lot of behind-the-scenes maneuvering too. But anyway, we prevailed. Turned out okay. Well, I've kept you an extra 5 minutes.